Okay, for part two on collisions and momentum, we're going to talk about glancing collisions, part two. So glancing collisions are compared to first, we were talking about collisions in actually one dimension. These are two-dimensional problems. They can be either what we call elastic collisions or inelastic collisions. Elastic collisions, you don't lose any energy through the collision. The kinetic energy is conserved. In an inelastic collision, especially a perfect inelastic collision, the energy is not conserved. The momentum is conserved. So for elastic, we have the momentum conserved and also the kinetic energy. In an inelastic collision, momentum is conserved, but not the kinetic energy. So let's look at a problem. We have two balls that their initial state is the red ball is traveling at 10 meters per second towards the blue ball, which is a little bit off the axis there. The blue ball is at rest. And then after the collision, we have two velocities that we need to find, the red ball's velocity and the blue ball's velocity. We're already given the angle trajectory of each ball, so that helps us solve the problem. We also know that the masses are all equal. So momentum for the y-axis is conserved, so finding this, our first actually equation, because we have two variables we have to find, so we need two equations. So we'll start with the y. We have conservation of momentum, and this is all going to be equal to 0 because we don't have the any momentum actually in the y-axis that's going to figure into our answer, except for we can derive a equation here which we will need. So we just take this equation and we solve for VB, the blue ball's final velocity. That's what we're solving for right here. So let's look at momentum on the x-axis. It's also conserved. Okay, and so we plug in the values, and all this is going to be equal to the mass, of course, whatever that is, of the initial red ball's velocity, which, if you remember, was 10 meters per second. So then we can cancel out all the masses. We don't need the masses. Each term can be canceled out, and we get this expression right here. And all we need to do now is to factor out V of RF. And then we'll have an equation that will help us, that will solve for the red ball's final velocity. So now we have our two equations. Earlier on, we figured out the blue ball's velocity, and now we have the red ball equation for velocity. So let's just plug in our values, and we get for the red ball 7.66 meters per second, and the blue ball is basically from up here, it's just 8.839 times the velocity of the red ball final, and we have our answer to the blue ball. So we have the red ball and blue ball velocities. And by the way, this is energy is conserved, and so is momentum. Now let's talk about inelastic collisions. These are a little bit different. First of all, in this diagram right here, we see that we have two vehicles approaching an intersection that have a collision. On the right, we have the same thing, but we have the blue car that's off axis a little bit. This problem right here on your left is much easier to solve than this one. So let's take a look at it. Okay, so what we're going to do is the same thing. We're going to do axis by axis, the x and the y. So the momentum for the x-axis is going to be equal to just mass times v. A little dog barking there. So back to the x-axis, and we have the initial and the final conditions on the x-axis. And all we need to do now to find an equation is to equate these two because they're equal. Okay, and so we do this right here. We equate them, and we're going to solve for v of xf. Okay, and so now we have one of our equations. For the y-axis, we're going to do basically the same thing, and we're going to get our velocity on the y-axis. Okay. So we're going to use, we need to find the magnitude. So we do have two component vectors of velocity. So we can find the magnitude by using that. And then to find the angle, which is going to be from the positive x-axis counterclockwise, we can use our inverse tangent to find the direction of velocity. Okay. Now we're going to do examples, but let's now talk about the non-perpendicular or off-axis collision. We have a phi of 125 degrees. What is this telling us? Well, this is telling us that the angle from the positive x-axis is 125 degrees. And then we have our collision. This is inelastic, so both vehicles will stick together as one velocity. Get rid of that. And so for our v prime f, the component, this part is one of the extra components that we didn't see on the perpendicular collision. So this is actually, we're going to have the x going this way too, and this is actually going to be a negative, so it's going to take away from that. We'll see that a little later on. And so this is basically our equation for this angle right here. Cosine of phi equals Vx of f divided by V prime f. And then our sine component for this extra part here is going to be equal to this right here. And that's this right here. Okay. So let's look at, for the x-axis, we have M1 and V1, and then we need this component of car 2, the blue car. This is M2 V2 cosine phi. And then we have our final. We need to equate these two. We get this expression, and then we get the equation we need to find one of the component vectors, Vx of f. And do the same thing for the y-axis. What's happening on the y? We have M2 V2 times the sine of phi. Actually, we're only concerned about this direction here. And then we have the final momentum, and this is the final. We equate these two. Here's our expression after we equate them. And then we have our equation. So we have two equations, one to find Vxf and one to find Vyf. So now we can find V prime. So V prime is found by taking the sum and square of the two component vectors to find the magnitude, and to find the direction of V of f, we'll use the inverse tangent. Okay, now let's look at numbers and solve some of the problems with using values. In this case, we have a perpendicular collision. We have a red car and a blue car. It tells us our masses of each car. and it tells us the initial velocities, and it says find the magnitude and direction of both cars after the collision. So the first thing you want to do is you want to make a summation of the x momentum, the initial. The second thing you want to do is you want to make an expression for the x momentum final. You're going to equate those two, okay, and then you're going to get this expression, and you're going to solve for Vxf. Okay, and when we do, we get an answer of 8.0 meters per second. Now that's on the x-axis. Now let's continue on to the y. The y is momentum in is going to be equal to this value right here. We just basically take m times v, and the final will be the total, both masses, because it's a inelastic collision, with this answer. Now you notice it says 55 kilograms times VYF. Okay, then we equate those, we get this expression, and we need to solve for VYF. Okay, we have that here, we get this right here, and we get 9.6 meters per second. So we have our VXF and we have our VYF. Let's find our magnitude. Our magnitude is 12.5 meters per second. The velocity of both vehicles stuck together. And then we can find the angle. And our angle is 50.2 degrees. Now, this angle is in the first quadrant because both x and y are positive values. So we know this is 50.2 degrees. And it would be from east or from 0 on the Cartesian coordinate system. Now let's look at one where we have an off-axis issue problem, and one they give us our masses and of the cars and our velocity, initial velocities, 12 and 21. So this is car M1, this is car M2 over here. So 2, 1. Okay, so let's do the x-axis. The momentum will be equal to this. Now this part right here is from the X car itself, and this is the part that is from the blue car. Okay, it's going to actually add summation to this right here. So it's actually, this is actually going to be a negative value, and it's going to take away from the momentum of this car right here. So let's plug everything in, and we get this value right here for the initial x. Then we need to find the final. Final x is going to be equal to the combination of the masses, and that is 3,450 kilograms times VXF. We don't know what VXF is. We're trying to find that. Okay. So now we equate the initial momentum and the final momentum, and we solve for VXF, which we do right here. And this is what we're solving for. Plug in the values and we get our answer. And this is a negative 3.33 meters per second, which is going to give us, tell us in what quadrant that this collision will occur. So let's look at, for the x-axis, what's happening. We have M1, V1, the momentum contributing from mass 1 is in this direction, and then we have the momentum contributing to the x in the opposite direction. So we'll have this vector minus this vector. The y, all of it is, actually the y component of this vector is going into the y. We have nothing in the x. So we have For the y-axis, we'll use m2, v2 sine theta, and for the x, we're going to use m1, v1 plus m2, v2 cosine phi. So let's do the y-axis. And we get a value here. And now let's do the final on the y-axis. Again, we need to find out what this is right here. We take the two equations and we equate them, and we solve for v sub yf. And we get 10.9 meters per second for y. So now we have both y and x. So if you notice that the x component is negative and the y isn't. So this is automatically telling us this vector is going to be into the second quadrant. Okay, so it will be right in here. Okay, so we'll solve for the magnitude, 11.5 meters per second, and then we need to solve using the inverse tangent to find the angle. Now when you plug this in to your calculator, you're going to get a negative 73 degrees. This is not the correct answer. Okay, you're going to have to add 180 degrees to it. This negative 73 is actually what it's doing. It's coming from the negative axis size and going clockwise, like this up here. And so our angle is somewhere around here, and then we need to actually calculate this angle right here, which is 107 degrees. So basically, if you just add 180 degrees to that, you will get the correct answer. This will not be the correct answer. So you want to make sure you do this right. Okay, and so this is just saying the same thing. Let's look at another example. This is a perpendicular problem, so it's pretty easy. And first of all, we take the x-axis, the initial momentum in, and then the final momentum out. We equate these two answers, and we get this expression. And then we solve for Vxf. This is our Vxf. And then we continue with the y. Okay, so, and we go through and we get our equation by equating those two, and then we solve for Vyf. So we have 15.6 meters per second for the final velocity, and then we have the angle, 42.7. Because both of these are positive right here, we don't have to worry. This is going to be into, what's this? This is right here, sorry. I'll get rid of that. So we have 10.6 meters per second. This is the y, and 11.5, that's the x. Now let's look at an off-axis. And we're going to start with the x-axis again, m1 times v1 plus m2 v2 cosine phi. They're giving us a phi of 135 degrees. And then the final on the x. And then we're going to equate these two equations. And then we're going to solve for Vxf. And when we do, we get a negative 4.31 meters per second. So let's do the y-axis now. And we get, we solve and we get our momentum actually for the y-axis. And now we're going to solve for the final. This is where the two masses are stuck together. And we're going to solve for VYF. And we get 8 meters per second. So, plugging everything in, our V prime F of both vehicles is going to be 9.10 meters per second. Our angle is going to be negative 61.7. And now you're going to have to take that because we know, because the x is negative, that the collision is going to happen in this quadrant right here. So we're going to have a vector here. So we need to add 180 degrees to what we get on our calculator. Okay, and that ends chapter 6. There will be some problems that I may do in addition to these part 1 and part 2.